All right, this is our 5.5 lecture for calculus. We've already talked about how to do derivatives and integrals of the natural logarithmic function where your base is an e. This lesson focuses on what if the base is not e. So when the base is something other than e, those are the formulas that we'll focus on today. So our learning intention hasn't changed. It's still to derive and integrate a variety of functions. And our success criteria specifically for today is to derive and integrate functions of the form y equals a to the x. In other words, instead of, in the past this has been an e, so this could be a 2, a 5, a 1.3, could be anything other than e. And then also functions of the form y equals log base a of x. So we've already done when the base was an e, we had the L, we knew how to do the derivative of an ln x or a integral. And so that's what we'll be focusing on today. So once again, you're going to need page 4 from your math Bible. And we already have used these top 3 derivative formulas. We'll be adding in for lesson 5.5 these two. So the derivative of a number to the x power is that number to the x power times the ln of that. So if I was doing 5 to the x power, it would be 5 to the x times ln of 5. And of course, if this is more complicated than just an x, we have to use the chain rule as well. The other formula that we'll be doing derivatives for is log base a of x. So if this is log base 5 of x, we'll have 1 over ln 5 times 1 over x. And if this is more complicated than just an x, then of course we have to use the chain rule. So if this is an x to the second, I would have an x to the second here, and then multiply times the derivative of x to the second. As far as integration goes, we only have one new formula. We've already done these 3, so we're adding in this one today. So if you have an integral with an a to the x in it, then you will have a to the x over, so for example, it was a 5x, you would have 5 to the x power over ln 5. So instead of multiplying by the ln 5 like you did here, this is just the inverse, so we would divide by the ln 5 here. And so we'll just basically be finishing up this section of formulas for page 4 in your math Bible. All right, so let's get started. Our example 1, I've actually got a couple slides over here. Here's example 1. We have y equals x times 6 to the negative 2x power. So if I'm doing a derivative and my function has two things multiplied together and those two things both have an x in them, that means I have to use the product rule. So product rule means I need a u and a v. So my u is going to equal x, and my v is going to equal 6 to the negative 2x power. So u prime, like always, will be just a 1. And v prime, this is a new derivative for us here. I have a base of 6 and a power of negative 2x. So this is going to require the chain rule because this is more complicated than just an x. So let's go back and look at our formula again for an a to the x. The derivative of an a to the x is itself times ln of a. Itself times ln of a, and of course if this is more complicated than just an x, I would also have to multiply times the derivative of that. Alright, so here I have my a being a 6 and my x being a negative 2x. And I'm probably going to need just a little bit more room for this, so I'm going to shrink that down. Alright, so the derivative of a to the x is a to the x ln a. So I'll write that down here just so we have it to look at. Derivative of a to the x power is a to the x times ln of a. And then, of course, if this is more complicated than just an x, I have to multiply times the derivative of that as well. That's just the chain rule. So I'm going to have 6 to the negative 2x. In other words, I just keep this part the same, just like it was here. And then I multiply times ln of a, and my a is a 6. So that's times ln of 6. And because this is more complicated than just an x, I have to multiply times the derivative of that. And the derivative of that would simply be negative 2. So if I simplify that, really, I can't take this negative 2 times any of this, so that's just all my v prime. I have an ln 6, a negative 2, and this. I could put the negative 2 in front of the ln 6, I guess, so that it reads like this, 6 to the negative 2x power times negative 2 ln of 6. Might look a little bit better that way. All right, so there is my all the things I need to do the product rule. So once again, this was my u, this was my v. My u prime is easy, my v prime is a little more difficult. It's just this itself times ln of 6 times the derivative of this, since it was more complicated than just an x. So my y prime is going to be u prime v plus v prime u. U prime v plus v prime u. So u prime times v is just 6 to the negative 2x power plus v prime u. Here's my v prime, here's my u. So I'm basically just taking x times all of this. So I've got x, or let's say 6 to the negative 2x times negative 2 ln 6 all times x. So my y prime, I could take this negative, put it out here and make it a minus sign. I could stick this x in here with this 2 maybe to look that make that look a little bit better. And I said I was going to put that negative out here. So there it is. And inside here I just have a 2x ln 6. And so really that's an appropriate derivative in itself right there. When you go to check it in the back, it might not look like that. So I'm going to factor out the 6 to the negative 2x that both terms have. Both terms have that, so if I factor that out, my first term would just be a 1, because this times this has to equal this, and then minus 2x ln 6. And then it's possible that they might even put that 6 to the negative 2x into your denominator. So the answer might look like this: 1 minus 2x ln 6 all over 6 to the positive 2x. So not sure which way they would have it. I would be fine as an answer for anything from here down. That's an acceptable answer, that's an acceptable answer, that's an acceptable answer. So any of those would be good. And that is our example 1. All right, example 2. We have, once again, two terms multiplied together. Both terms have an x in them, so I'm going to need a u and a v to do this problem and to use the product rule. I'm trying to do a little more difficult examples than I normally would do, just because I want to do the harder ones with you so that you can do the harder ones on the homework. So a u is equal to my first term, which is 5 to the negative x over 2, and v is equal to sine of 2x. And so this one is one we've done in the past, so we'll do v prime first. V prime, the derivative of sine is positive cosine. And since this is more complicated than just an x, I have to multiply times the derivative of 2x, which would be 2. So my v prime, if I put the 2 out front, is 2 cosine 2x. All right, my u, remember this is the new one that we learned today. This is a to the x, or a to the u. So that's this derivative right here. Derivative of a to the x is itself times ln of a. So a is this thing right here. And so the derivative of this is going to be itself times ln 5. And then because this is more complicated than an x, I'll have to multiply times the derivative of that as well. And maybe I should write that as a negative 1/2 x, just to make it a little more understandable as to how you would take that derivative. All right, so u prime, we said is going to be a to the x, so we just write down what it originally was, but then I have to multiply times an ln of 5. And because this is more complicated than an x, I have to multiply times the derivative of this as well. And the derivative of that is just a negative 1/2. All right, so I guess isn't a super easy way to write that, but we'll try and stretch it out here a little bit and make it look a little nicer. Let's put the negative in the very front, and then the 5 negative 1/2 x, and then the ln 5. So that will be my u prime simplified. Alright, so let's shrink that up so we have a little bit of room to write our derivative. So this is what I'm using for u prime, this is what I'm using for v prime. Here's my u, here's my v. Alright, so I first of all need to do u prime v. So I'm going to take u prime times v plus v prime times u. So u prime times v, let's see, this was originally a g of x. So g of x is going to be u prime times v, which is sine of 2x, plus v prime u. And I'm going to put the u first to be consistent with both terms. Times 2 cosine of 2x. So this is the v prime, and this is the u. There's the u prime and the v. So u prime v times v prime u, or plus v prime u. And once again, that would be acceptable to me as an answer. I'm not sure if that's what they would have in the back of the book when we checked it, so because of that, I'm going to factor out what the two terms have in common. That's a g prime. The two terms in common have a negative 5 to the negative 1/2 x power. That's the only thing they really have in common, so what will I be left with if I pull that out? I will have a ln 5 sine 2x plus 2 cosine 2x. And once again, this could be shoved down to the denominator to make that power a positive power. So g prime of x might be written as ln 5 sine of 2x plus 2 cosine of 2x all over 5 to the positive 1/2 x, and we still have this negative sign here, so that might be written out in front of the entire thing or just on the bottom. I'm going to put it down there. So any of those last three statements for g prime of x would be acceptable answers to me. Alright, so with that being said, let's move on to example 3. Example 3, this time we have a logarithm that's got a base of 5, and we have several parts to this logarithm. So first of all, let's go look at the derivative formula for a log back in our math Bible. Right here, that formula is log base 5 of, we obviously have something way more complicated than just an x, so we're going to have to use the chain rule. But if we didn't, it would just be 1 over ln of a, in this case our a is a 5, times 1 over x. Remember, this is our x, and then ours is more complicated than that, so we have to multiply times the derivative of that. Now, would it help us to use our rules for logarithms to simplify that? I would definitely say so. I would want to use my rules for logarithms. I think I can write like 3 different logarithms in this problem by separating these out. First of all, I would use rule number 3 that says when you have division, you can make it subtraction with 2 logarithms, and then I can change the multiplication to 2 separate logarithms. So let's first of all just rewrite this problem before we even take a derivative. Let's say log base 5 of 4 minus log base 5 of x squared times 1 minus x to the 1/2 power. That's how I'm going to write it. So all I did was take my logarithm with division, change it to 2 logarithms with subtraction. So I'm good with this one, but over here, this one can be separated into 2 logarithms. And remember that this minus sign right here is going to have to be distributed to both. So log base 5 of 4 minus, I'm going to do a bracket, log base 5 of x squared plus log base 5 of 1 minus x to the 1/2 power. Okay, so now I need to distribute this negative to both logarithms, and I'm also, while I do that, I'm going to take these powers and move them out in front of the logarithm so that we have something that will be a lot easier to take a derivative of. So distribute the negative. Oh, I forgot to move my 2 out front. Let's do that real quick. So I've got a 2 out front, log base 5 of x. Distribute this negative, so that becomes a minus 1/2 log base 5 of 1 minus x. And so there we go. We have 3 separate logarithmic terms, and I'm basically going to find the derivative of each one of those. So derivative is what I'm ready to find now. Let me shrink this up just a little bit. And now I can use my derivative rule on each of these separately. Now, don't be confused by this one. There's no x in this term. If there is no variable in this term, that means it's a constant. Log base 5 of 4 means what power would you put on a 5 to get a 4? And I don't know that off the top of my head, but we could find that out in the calculator. It's that whatever that is, it's just a constant number. And the derivative of any constant is 0. So when I go to find g prime of x, the derivative of the first term is just 0 because that's a constant. The derivative of this term, I'm just going to take that negative 2 and carry it along. And then this log base 5 of x is a formula straight from the Math Bible. I don't even need to use the chain rule. If you look here, I have a 5 here and an x here. So it's going to be 1 over ln 5 times 1 over x when I apply that formula. So we're ready for the second term. My negative 2 is just carrying along. The derivative of this, we just said was what? 1 over ln 5 times 1 over x. 1 over ln of 5 times 1 over x. Okay, so that's my grouping just for the second term right here. Okay, next term, the minus 1/2 is going to carry along. And this time, everything is exactly the same, but instead of an x, I have a 1 minus x. So it's going to look just like this, but instead of an x, I'm going to have a 1 minus x, and then I have to multiply times the derivative of 1 minus x because I have to apply the chain rule. So my negative 1/2 came right here. The derivative for a log base 5 is 1 over ln of 5 times the derivative of 1 over 1 minus x, and the derivative of 1 over 1 minus x is simply negative 1. So I have to use this is the chain rule here. I should not have an equal sign there. That's a multiplication symbol. Multiplied by negative 1. This is more complicated than an x, so I have to multiply times the derivative of that. The derivative of that would be negative 1. Okay, so now to simplify this, let's just leave off that 0. I'm going to multiply all of this together, and if I do, I am going to have negative 2 over x ln 5. Makes it look a little prettier. And then the second term is all of this. So I have this negative out front, this negative on the end, so that can make a plus sign. And looks like I'm going to have a 2 ln 5 times 1 minus x. And you can write those in any order that you want. But that, at this point, would be my answer. If we wanted to find a common denominator to possibly match an answer that might be in the back of the book, it may just look like this. But if we had to find a common denominator, looks like in my common denominator I would need a 2, I would need an x, I would need a 1 minus x, and an ln 5. So that's everything that would be in my denominator. So what would I have to multiply this times? To get this, I would need a 2 and a 1 minus x. So if I take the numerator times a 2 and a 1 minus x, I would have something like this. And then what would I have to multiply this times to get the common denominator? Well, it looks like I would just need a straight old x. Everything else is in there, so if I multiply this times an x, I would have a plus x. And so, to simplify that just a little bit more, my numerator would be negative 4 plus 4x plus x, because I'm simply distributing this negative 4 to both of these. So now I have my denominator. You could distribute there, but I think I would probably just leave it the way it is. Typically they'll leave denominators in factored form a lot of the time. And so one more step, putting those common terms together in the numerator, I would have negative 4 plus 5x all over my common denominator, which is 2x times 1 minus x times ln 5. And so you may see the answer written like this in the back or like this. It doesn't matter to me either way. I would accept either one of those. And that was our example 3. All right, example 4. On this problem, we're going to find a derivative and then actually find the equation of the tangent line. So I want to know what's the equation of the tangent line, the line that's tangent to this curve at this point. So this is a point on this curve. If I plug pi over 2 in for x, I should get a 1 out. So I want to know the equation for the line tangent to this curve at this specific point. So to figure that out, I'm going to need to use point-slope form. Point-slope form, here's the point, but I need the slope at that tangent line. And how do we find the slopes of tangent lines? We use derivatives. So my derivative for this thing, how am I going to find y prime if this is a y? Well, notice that you have an x in your base and an x in your power. So anytime you have that, it's a good idea to use logarithmic differentiation. And to use logarithmic differentiation, we're going to use one of the rules for logarithms that says you can apply a logarithm to both sides. So I'm going to apply a logarithm to both sides of this function before I ever take a derivative. Okay, that's a legal mathematical move. I can take the logarithm of both sides. And the nice thing about that, it allows me to take this power and move it out in front of the logarithm. So if I move that power out in front of my logarithm, now I have something that looks like this. 2x ln of sine x. Because I really don't have a, I could use my, I don't really have a derivative formula that's got an x in the base and an x in the power. So this allows me now to separate these. Now I can use a product rule for these two. And basically I'm using implicit differentiation because when I take the derivative of this, it's not just a y, it's an ln y. So I'm going to do implicit differentiation here with respect to x. And so because anytime let's see, what's the derivative of an ln? Derivative of an ln is 1 over the object of the logarithm. So in my case, that's 1 over y. But because it's a y instead of an x, I have to multiply times y prime. So that's going to be 1 over y times y prime. And over here, I'm going to use a product rule. This will be my u, and this will be my v. So let's see if we can work that out. Over here, let's shrink this down a little bit so I got a little more space. So my u is going to equal 2x, and v is going to equal ln of sine x. So how do I do this? One's the simple derivative. The derivative of 2x is just 2. But v prime is a logarithm, and we just looked at the logarithmic derivative. It's 1 over the object of the logarithm times the derivative of this because it's more complicated than just an x, so applying the chain rule. So basically it's going to be 1 over x times the derivative of sine x, which is cosine x. Or you could write it as v prime is cosine x over x. Alright, so if I apply that, alright, so I shrunk this up a little bit here, but if I'm going to apply the product rule to this right here, this is my u again, this is my v, so I need to take u prime times v plus v prime times u. So u prime times v will simply be 2 ln of sine x plus v prime u. V prime times u is 2x times cosine x over x. And I did put the u first instead of, here's the v prime times u. And then these x's are going to cancel. So I will cancel those x's out. And so now I'm just going to write this first part as a y prime over y is equal to 2 ln of sine x plus 2 cosine x. Alright, so now to get y prime by itself, I would want to multiply times y. And so if I multiply times y, then I have y times 2 ln of sine x plus 2 cosine x. So I have a couple of options here. Remember my goal. My initial goal was I wanted to find the equation for the tangent line at this point. And to do that, I need to use point-slope form. I've got my point. I need my slope of the tangent line, and that's what a derivative finds for you, is the slope of a tangent line. So rather than plugging y back in here, I have the y value. I'm just going to replace y with 1 and x with pi over 2, and that will find the slope for me. If you would rather replace y with this and then plug in pi over 2 for each of these, you can, but that makes it more complicated. So let's keep it as easy as possible. Y prime of my particular point is going to be, I'm replacing y with what y is equal to, 1, and I'm replacing x with pi over 2. Okay, so if I work that out, that will tell me the slope of my tangent line. Okay, well, I need to calculate sine of pi over 2 and cosine of pi over 2. So if you remember back to that's a quadrantal angle. Pi over 2 is right here. And pi over 2, let's see, I need this point, which is 0, 1. That point at pi over 2 is 0, 1. Remember that sine always acts like y, and cosine always acts like x. So the cosine of pi over 2 will be this x value, and the sine of pi over 2 will be my y value. So right now I have y prime, which is my slope, being 1 times 2 ln. We said that the sine of pi over 2 was the y value, which is a 1. So that's ln of 1 plus 2 times the cosine of pi over 2. Cosine's x, and x at that point is a 0. So now basically this disappears, and I'm left with 1 times 2 ln 1. So I have a slope of 2 ln of 1. Now if you think about ln is really a log base e. So what power would you put on an e to get a 1? What power would you put on an e to get a 1? That power would be 0, because e to the 0 is 1. Alright, so all this comes out to be 0, and I've got 2 times 0, which is 0. So that tells me that my slope is 0. So I have a line that goes through the point pi over 2, comma 1, and the slope of that line is 0. So we can use point slope form at this point, or you can just recognize, hey, this has got to be a horizontal tangent. This is actually an extreme. We're actually finding a local max and min here, or min, whichever it may be. But this equation, I was asked to find the equation of the tangent line at this point. That tangent line is going to be horizontal and go through this point. So horizontal lines cross the y-axis. It's going to cross the y-axis at 1. So you could say that tangent line is just y equals 1. Now if you'd rather go through the process of point slope form, y minus y1 equals m times x minus x1, you definitely can do that as well. Y minus 1 would equal 0 times x minus pi over 2. And then if you simplify that, this goes away, the 1 moves over, and you're still left with y equals 1. So our goal was to find the equation of the tangent line at the point pi over 2 comma 1. That tangent line will be y, the horizontal line, y equals 1, and we're done. All right, moving on to our last example. Take that back, we got 2 more examples. We're going to move on to integration, which actually may be a little bit easier. Integration, we have one integration formula, one new one. But I would like to point out to you before we go back and look at that formula that I'm integrating 2 terms here so that I can separate those 2 terms into an x cubed dx plus the integral of 3 to the negative x dx. Now, these look very similar. We have an x cubed and a 3 to the negative x. We're just kind of trading places there, but they have very different integration formulas. This is just backwards power rule over here. We've been doing this one since January. This one's new. This is the integral of a to the x. And I do have a negative in there, so I'll probably have to use a u. But yeah, I'm using this integration formula right here. The x cubed is the backwards power rule that we've been using all along. We just add 1 to it and then divide by that. This one is going to be a to the x divided by ln of a. So I have a 3 here, so 3 to the x over ln of 3. But remember, my x is negative, so I'm going to have to use a little bit of a u for that if I want to. Okay, so the integral for this one is simply going to be, don't need my integration symbol if I'm going to integrate. So this one's going to be x to the 4th over 4. And now I still need to integrate this one. Remember my integration formula for an a to the x is a to the x divided by ln of a. All right, so since I have a negative on mine, I'm going to say let u equal negative x. And the derivative of u with respect to x will be a negative 1. So that means du, negative du is equal to dx if I multiply both sides by a dx. So now if I go substitute that in right here, I'm going to have 3 to the u du. And now this works with my integration formula because I now just have a u, so I can say that my integral or antiderivative of this is 3 to the u over ln of 3. So I still have x to the 4th over 4 plus 3 to the u over ln of u plus c. But I need all x's in here, so I'm going to go back and replace my u with a negative x. Both u's with a negative x. Oh, I'm sorry, I did that wrong. That's not u, that's my a value. My a value is a 3 in this case, so I should have a 3 right here. ln of 3. All right, so just replace that u with a negative x. So I have x to the 4th And I forgot the negative here. This dx is equal to negative du. So this dx got replaced with a negative du. So I'm just going to shove that negative out here, which means this plus sign can become a negative sign. All right, so I have x to the fourth over 4 minus 3 to the negative x over ln of 3 plus c. And that's my answer. So really when the only thing that's keeping this from being an x is a negative sign, it is okay to, if you just understand that conceptually, that that's going to change this sign, and that in the end, that's fine, you could do that. I just kept this here, but that changed the sign out front. Essentially, I'm dividing by a negative instead of multiplying by a negative like I would do in the chain rule. Because this whole process is just undoing the chain rule, right? So chain rule typically means to multiply by a negative, so if I divide by a negative, that would put the negative here. And so that's your final answer for example 5. All right, example 6, and this is our last example. I'm doing an integral with a sine and a cosine in it. I don't have any integral formulas that look like this, so I'm probably going to need to use a u. I do have a formula for 2 to the u or 2 to the x. So maybe I could let this be my u or this be my u. I would say let this be your u, so that way when you plug it back in, you have a 2 to the u. So let's say u is equal to sine of x. The derivative of u with respect to x, the derivative of a sine is simply a plain old cosine. And that works out really well. If I multiply both sides by a dx, I've got cosine of x dx, which is great because I have a cosine of x dx in my original problem. So that can be replaced with a du. So now when in the process of changing this to u's, remember this is equal to u. So I can make that 2 to the u, and this is the same thing as du. So I have 2 to the u du, and I have a formula for that. My formula just has x's in it. Remember, I used it in the previous example. The formula was if you have a number, a constant, to the x power, then it's a to the x over ln of a. So my integral, or my antiderivative of this, is simply going to be 2 to the u over ln of 2 plus c. So 2, remember u is a sine x, so I go back and plug that sine x in for 2 over ln 2 plus c, and that is your answer. 2 to the sine x over ln 2 plus c. So the integration on these is actually a little bit easier than the derivatives, if you ask me. And that's your last example. Good luck with 5.5. Please let me know if you need help. Remember, you can contact me via text, email, or simply call me. I can set up a Zoom meeting with you individually, or we can meet during our normal scheduled time.